All right, I'm going to start back at the Big E cheese whenever I was deriving this and I stopped so that we can actually finish the derivation. That's what we're going to start with. And then after that, we're going to try to move on. And I'm going to try my very best to try to describe this to you guys without using calculus. So that's the game plan. No calculus. Think back to whenever we were looking at the if you guys look at the object just kind of moving around in a circle, at any particular point, we've already said that the velocity is constant. It doesn't change. So the VI and the VF, but yes, there is acceleration. Totally true. The VI and the VF are always the same thing. So this VI right here, whenever we're talking about the difference between two velocities in calculating the delta V, this VI and this VF are the exact same thing. So we could just end up saying that VI is equal to V, like the actual velocity. And we could also say that the VF, whenever we're finished, is also equal to V as well. Okay? If we were to try to calculate the delta V in our traditional sense, we would get that the change in velocity is zero, which kind of makes sense to us because the velocity is really not changing. The delta V is constant, so it just comes out to be zero. So that actually makes a whole lot of sense to us that the velocity doesn't really change at any particular point in time. You also have to keep in mind, and the hard thing to remember about this is I know this looks like it starts at the center, but what we're actually trying to do is we're taking two vectors, VI and VF, and we're subtracting them from each other. And when you subtract them from each other, you have to take the dots and you have to put them in the same spot. You have to put the heads away from the tails of the arrows to get the actual direction of the delta V. So they do end up being the same size. Yeah. But whenever if they have two different sized vectors, then whenever you try to add them or subtract them together, then they don't necessarily come out exactly the same. Okay? And we were also saying do what? Yeah, technically like an ellipse. I could go for that. I could definitely go for that. You could do the exact same argument with, and this is where I kind of tripped up last time. You could do the exact same argument with the radius as well too. And it almost makes too much sense whenever you think about it, and that's why I skipped it last time. Because if you're dealing with the radius at one location and the radius at another location, the difference between the two, so like this is the distance that we were traveling at the beginning, so this would be the initial radius, and this would be the final radius, and the distance between it would be the delta r. But it's the same radius because the length of the object going in the circle isn't changing. So the length of the initial radius is just r, and the length of the final radius is also just r. Because of this, what ends up happening is we have two similar triangles. So the angle that's caused by this VI and VF is the exact same angle that's being caused by this RI and RF, this initial radius and this final radius value. So what that gives us is it gives us two isosceles similar triangles, okay, which we can then use using a geometry argument that these things actually work, okay? So I can say because they have a so these two sides, here's the isosceles part. VI and VF are identical to each other. So these are the two similar sides, or sorry, these are the two equal sides to the isosceles triangle. And then if you're dealing with RI and RF, these are the two uh, equal sides to the isosceles triangle. So there, and you can kind of see that it's like similar angle, theta, similar angle, equal angle, theta, equal, I keep saying angle, equal side, theta, equal side, theta, equal side. So these are our similar triangles. We can use that to our advantage just by setting up a proportion And we can say that, let's see, delta r over r, and that would be like this guy, this side of the triangle divided by the radius. Let me go ahead and use capital R because I already did it over here. So delta r over r is equal to delta v over v. Okay, so here's delta v over v equals delta r over r. So right here, this is really just coming from similar triangles. Okay, we have, um, we know that the acceleration is equal to delta v over delta t. I had written that one last time right here, and I'm probably going to rewrite it because I already put a bunch of crap in the way. So I'm going to rewrite it and give myself a little bit more space. Because what we can do is I can say, oh, okay, well, if it's delta v over delta t, acceleration equals delta v over delta t, um, this delta v right here can be solved. And I can just say that, well, delta v is just literally delta r over r times v. Okay? I can also, hang on, I might have to, yeah, v over r times delta r. Okay, I'm in the right spot. So now I can substitute this in. So this delta v, I can use this to plug it in down here. Yeah, this is where things get exactly. This is where it gets really hairy. So it's v over r and delta r, and then there's also a delta t down here too. So these three things, this one, and this one, came from over here. Okay, so the only thing that's left is this delta t, and this delta t is down on the bottom. Okay, and then what we're going to do is now we have to make a logical argument to ourselves, and we have to say, okay, well, if we're moving down, and we just say that if this delta t, if this gets really, what if this is really small? What if this is just so small that the time difference doesn't really matter? Okay, and if it gets so small that the time difference doesn't really matter, then what you have right here, this delta r over delta t, well, it's not null, it's a speed because it's distance over time. So what if this is really, 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 really tiny? What you're getting is you're getting a really, really small snapshot of the speed of the object. So how far you're actually moving in such a short amount of time. So this expression right here down at the bottom, this entire expression is the velocity, the instantaneous velocity. So instead of this being v over r times delta r over delta t, we just shorthand this and we say that AC is equal to v squared over r. And that is how we actually get the centripetal acceleration, and hopefully you never have to do that again. Okay? Hopefully you never have to do it again. But it's good to go ahead and put it in there in case on the AP Physics test they give you an open response and they're like, "Oh, by the way, how do you get this?" But that's pretty deep. I don't know. I don't know if that would actually happen, but just in case, I always want to make sure. If you are in calculus, what we just did was we're taking a limit as delta t approaches 0. And that's supposed to look like a triangle, but that kind of looked like an eyeball. I'm sorry. Like that. It's the yeah, it is basically so like the limit as delta t approaches 0 is going to be really, really, you're looking for at the derivative basically. Okay, yeah, is what you're looking at. And the change, yeah, the change of the radius with respect to time is the derivative function, and that's going to be the velocity. Okay, the derivative of the displacement function ends up being velocity. And that's how that actually works. And if a lot of us were in calculus, that is what I would have used instead. But I just have to think like, okay, well, what if our time gets really small? So your delta r is just really a velocity. Right, yeah. So we just have to we'll take it that way because like everything in physics you can do from an algebra standpoint or a calculus standpoint. They're just two different ways. Engineering definitely wants you to use a calculus standpoint because not everything is going to be straight lines. And the whole reason for doing calculus is because sometimes you have to deal with not straight lines. And calculus is really good at handling things that aren't like simple shapes like triangles or squares or things like that. If you try to do the same thing algebraically, it's really hard to do. Calculus actually makes that part easier. It's a powerful tool to make our life easier. It would make simple things more difficult. So, like for example, if you wanted to find the area of a triangle, you would just use 1/2 base times height, which is an algebraic expression. You wouldn't use the integral of the area under the curve, which you'll get there whenever you see it. Trust me. It's a lot more work for something really simple. So if it's a simple shape, you really wouldn't use calculus for it. If it's a complicated shape, you would use. You can. You can use both, and ideally, in a real world, you should use both. Like you're going to use the best one for whatever fits, right? So, like for example, if you've got, I consider calculus and algebra like screws in a nail. Like sometimes you need a nail, sometimes you need a screw. Which one is the best? I don't know. It depends on the situation. Okay, so like if you sometimes a nail will do the job just fine, and sometimes a screw will do the job just fine. But you don't necessarily want to use a screw for everything if you're doing like 500,000 screws. Like if you're making somebody's fence, you don't want to individually hand screw everything in there. You're going to get like carpal tunnel syndrome instantly. It's right. Okay. So, have we talked about centripetal force yet? I think have we talked about centripetal force with our um, lines of action? Yeah. Okay, that's true. Kind of. So I'm gonna write centripetal force. I think I mentioned it briefly. I really do think I mentioned it briefly because, like, I know that I said that force is equal to mass times acceleration. So this also applies to centripetal forces too. So the centripetal force can be written as mass times centripetal acceleration, or mv squared over r. Because the centripetal acceleration we just proved is v squared over r. So if we can find a centripetal force, that's equal to mv squared over r. And I do believe that I said that with you guys. So let's try to take that and let's move it into a different a different world. So like if we're talking about like free body diagrams and we were doing the same thing that we did yesterday in the lab where you took an object and you flung it around your head and we were to try to make a free body diagram of that object that was flying around in a circle, what would that free body diagram, oops, I said free body diagram, didn't I? Sorry. What would that free body diagram look like? What forces would we have acting on that object? Okay, so we would have, first of all, what's our system? The whole circle's the system? Okay. So the object, and then you want to include the person? Just the string. So just the string. Okay. So just dealing with the object and the string attached to it, we can make this entire thing one dot like this. Okay. What forces do I have acting on this? And since it's just one object, it doesn't have to be balanced forces. Okay. Because we're not, obviously, we're not looking at the entire system here. So just this object. We have tension. Okay. So I'm going to put tension going this way. And then what? Because tension's pulling in, right? Okay, where's the applied force pulling? Really? Whenever y'all were twirling this stuff around your head, did you push it? You never push the string. You never no, that's not a fat bet. You never push the string. It okay, so what would be centripetal force? Hopefully not quite yet. I'm not mentally prepared for centrifugal forces yet. Um, No, this isn't a centrifugal force, and the tension is the Newton's third law pair to the applied force. Okay, because when you're twirling this thing around, you are applying a force on it, and the tension and the applied force is a Newton's third law pair, but the force is not pushing the object out. The force is actually keeping the tension is actually keeping this in the circle. So the acceleration that's happening here, the force that's happening here from the tension is actually keeping it inside. So I'm going to say this, and here's how I normally write this. I normally write it as TC because I want to denote that this is a centripetal force, but I don't want to call it centripetal force. Okay, and the reason why I do that is because things can be either linear or centripetal. So tension can be linear, and tension can also be centripetal. So it really depends on if it's acting in a circle or if it's acting not in a circle. Okay? Does that make sense? Okay. So that's what we're dealing with generally. And also, there is a common convention, and I'm going to hope that I don't accidentally mess it up. If the force is going into the circle, that is considered negative. Okay. If the force is going out of the circle, that is considered positive. So negative is like pulling in, and positive is like pushing out. That is the convention that we use. Can you do that backwards and still get the problem right? Absolutely. Okay, but the general convention that we normally go with is that if you're going inside the circle, that is considered a negative acceleration, and if you're going outside the circle, that's considered a positive acceleration. And one of the main reasons that we do that is because of if you've got a vertical circle, gravity can play some issues with us. Okay. Now, speaking of gravity, y'all did miss one force acting here. The weight, you are not missing the applied force. You are missing the weight. Yeah. We are missing mg that's going down like this. Okay. So right now there are two forces acting on this object. There's the centripetal force that's keeping it in the circle, and you can't balance it out, okay? Because if you balance it out, it goes in a straight line. It won't curve. Yeah, go for it. Yeah, because if it's going in a circle, you have to have that unbalanced force to actually keep it in the circle. If you do this, which is not good, if you're like, we have an applied force right here, this doesn't work because if you did that, you'd be like this. I'm going to sling this around my head. Ready? Here we go. Whee! And it would just like go that way. Okay, why? Because you said that you have a balanced force this way and you have a balanced force this way. So why would it go in a circle? It wouldn't. Okay, it would just go in a straight line. And that's also something to say as well too. Since inertia is a thing, if a thing that is in circular motion ever has the force taken away from it, it will move in a straight line path that is tangent to the circle. So if you are dealing with something that is moving like this, and you lose traction, if it's a car going around in a circle and you lose traction, then you're going to take this path right along the tangent line. Okay, so really what happens here is this is just an object in motion wanting to stay in motion. So if the car is going around the corner like this, then it's going to, if you lose this centripetal force that goes in, if this goes away, and it's gone completely, you will just continue to move this direction. Okay. If one of those stoppers that's going around your head, if the string breaks, it's going to go in whatever straight line path that it got broken off from. Okay. Yeah, because this ends up making a tangent line at any point to the circle. Okay, ends up always making a tangent line to the circle. Fortunately, with circular motion, we don't have to do a lot of derivations or things like that because trig will become like super important then. So they kind of skirt over a bunch of it, which is very good for us because it's less traumatizing in general. But let's like try to think about a different situation. Let's see here. The um, think I've got a couple of pictures that I can go with. Ah, yes. What about this? If you have a stick, because I saw this a couple of times in the lab too, where y'all were actually making it go around, but the line was droopy. So instead of it going around in a circle straight above, your string was like this instead. And it just kind of went around, and it did do a circle, but your line wasn't straight out 90 degrees like this. Your line was like, I guess the best word I can come up with is droopy or a saggy line. Okay. What about that? At all? Yours was straight the whole time? I have video evidence. Are you sure? You're positive? Right? So, so this is going to be a little bit different, but not too different. One of the things that's going to be really handy for us is the measure of the angle between the two, between the horizontal line and the actual tension of the string itself. That's going to be a useful piece of information to us. So I'm going to write down that as the letter theta, or as my Greek boss would say back in Boston, theta. It's theta. And I would be like, okay. And then every time he'd walk away, I'd just say theta instead. Welcome to the South. This goes in a circle. So if I were to do this free body diagram, what two forces do we have acting here? Have what? What two forces? You Southerners? Gravity going down, right? What do we write for gravity? mg. Okay, we got mg going down. And then what do we have going up? Like this? Oh, cattywomp. Okay, cattywampus. We got a little bit of cattywampus here. All right. And it goes like this. So we're going to call this T. I like to call it TC, T centripetal. Okay. If you just call it, like there's going to be a lot of physics teachers that will just call it T for tension. But I like to put the little C down there to remind me that this is a, well, actually, you know what? Now that I think about this, I can't do that. I can't do that because that is not a centripetal, not a completely centripetal force. Okay, because by definition, a centripetal force is a center-seeking force. So my centripetal force is actually not completely the tension. It is not. It's not. No, you ain't. No, you're not thinking at this point. Okay, it can't be. This can't be center-seeking because the center of the circle doesn't go straight up like this. The center of the circle is right here, not up at the top. So I can't write TC here. So this actually helps me remind myself, okay, is this a centripetal force? And the answer for that one is actually not quite. It's close, but not quite. So I'm going to have to redo something here, okay? So where is my centripetal force? Like straight out like this? Okay. What is that? That's not a force. What is that? No. Okay, that is the x component, right? That is the x component of the tension. So we can call this Tx, and we can call this Ty. Okay? And this force down here, this force is the centripetal force. Okay? Not the whole tension in itself, but just the horizontal component of this force. Okay? Just the horizontal component of this force is the centripetal force in this case. All right? We can't use the whole thing. Now, in the line of action is going to be like just moving around inside this entire circle, and the line of action kind of loses its meaning aside from the fact that we're going to go in. We're either got to think, are we in the circle or are we out of the circle? So we really want to try to get all of our forces to either think in that either in the circle or out of the circle mentality. So, what pieces of information can we use from here? Because I think we can actually derive an expression for this. I think it's a good idea to. I'm gonna put my angle right here. Can we use kinematic equations? All right. Do we have the acceleration? Do we have the velocity? Do we have the displacement? There you go. So kinematic equations, bad idea. This is not the part of the tool belt that we want to use. Okay. Yeah, and you would need the acceleration too. We're dealing with forces. These are force diagrams. So if these are force diagrams, my first instinct is to go to the forces. What do I do? Well, I did. They're right there. I found the forces. What do I do next? Crying is an option, but we're gonna keep going. After you cry, okay, let's balance the forces. I'm ready. What are we balancing? Okay, okay. Obviously, I'll need more practice on this. Balance the forces. Because you have to ask yourself two questions. Is it moving? Is it moving? Yes. Okay. So it is moving. So that means that there is going to either be a constant speed or there's going to be some acceleration to it. Okay. So constant speed. So that means that the forces are going to end up being balanced. Okay. So there is some kind of net acceleration happening here, right? Good. Okay. So I can see that the the vertical forces are going to be balanced on each other. So this one and this one, Ty and Mg, those balance each other out. Tx is going to be an unbalanced force, okay? And Tx is also going to be centripetal. So I have to split these apart. I have to handle these in a y, and I have to handle these in an x. So we can do the y, or we can do the x. Which one would y'all rather do first? Which one's the easiest one to do? Uh, I think my brain just broke a little bit. What do you mean there's no acceleration in the x? This is going in a circle. This is going in a circle, right? So I think the way that we want to do this is I think we want to try to balance the y's out first, and then I think we want to do the x one. I think the y is the easier one, and I think the x is the harder one. So let's do that. Okay. All right. How do we balance? Wait. You just said to balance. You don't need the notes for balancing. Balance. You set them you set them equal to 0, right? Sum of the forces is equal to 0, okay? So in the y direction, the sum of the forces, we know since they're balanced, it's going to equal 0. We've got two forces here, okay? So mg plus ty equals 0. This is mostly correct. There we go. Yeah. So mg is pointing down, so that one's going to be negative, and ty is positive, so that's going up. So these are going to bounce out. And then Vernon, this is the way that you like to do it. The ty and the mg just end up balanced. So this is normally how you like to write it. Ty is equal to mg, like this. That's a little, don't need that dot there. I always like to write it from the sum of the forces equals 0, but whatever. Now ty can be something as well too. Well, this is the first time we've done this problem, Chief. So I mean, like, but in general, you balance them out because that's how you normally did that. That's how you did it on your homework. I think you have. Uh huh. You'd be like, joke's on you. I don't do my homework. Now, I don't want ty. I want, yeah, I need it in terms of tension only. So let's break that apart. So instead of having t and then having tx and ty, we need to break this down into its sine and cosine component. The vertical one is sine. Very good. And then this horizontal one? T cosine theta. Good. So instead of writing Ty is equal to mg, I'm going to write T sine theta is equal to mg. Okay. Now, we've got an expression. So if you want to find the tension in the rope, we're just going to have to solve for the tension. It's just mg divided by the sine of the angle, and you've got it. Okay. Now, that was the non-centripetal part. That's the easy part. Yeah, that's the easy part. Now we got to do x. Okay. Which actually isn't that bad either. So, is it moving? Okay, is there a balanced force? Why isn't there a balanced force? How do we know it's not equal to 0? Big brain isn't enough. We drew a picture. Is there another arrow going this way? Yeah. Some of y'all just want balance in the universe, and you want that other arrow to be there, but it's just not there. There's one force going this direction. So there's an unbalanced force acting here. There's an unbalanced force. So here's what we're going to say. We're going to say that the sum of the forces is equal to not 0. Don't write not 0, right? What's it? What is the not 0? You can't say yes either. That doesn't count. 1? That doesn't count. But we know that it's equal to something. According to Newton's second law, mass times acceleration. Okay? So we know that this is mass times acceleration. Okay, and what's the mass? We don't know. Hey, you know what? Even for that matter, what's the acceleration? We don't know. This whole thing is alphabet soup right here. The mass is m and g. The only thing that we know right now is that we're on Earth because it said g. So we at least know that gravity is 9.8 meters per second. But that's but not you don't use little g for it though. You don't use little g for it though. You don't use little g is specifically for Earth. Little g is specifically for Earth. Yeah. If you want to use acceleration due to gravity on different planets, you compare it to Earth. So you could say that like, oh, this is 4 Gs or 5 Gs or one a half or a half a G, but you don't actually use little g for other planets though. Okay. Yeah, but that's nitpicking. You could, I mean, like obviously you could do it and you would not be like completely incorrect. It's a notation issue. So like usually we don't use little g for other planets. Sorry, if I told you that way, then I misled you indirectly. Yep. That is true. Yeah, that is true. I haven't told him that though. I haven't told him that. Okay. Sum of the forces is equal to ma. Now, we know that acceleration is in a circle. We know that we're going in a circle, right? We know that we're going in a circle. So, yeah, assistant principal just comes in and mic drops y'all. Yeah, exactly. So we're going in a circle. So we know that acceleration can be written as another way because it's going in a circle. It's a circle. So we can, instead of writing A, we can write AC, which is okay, guys. Look, this isn't like I could do this. MAC. Okay, well that didn't really help me any because it's still the same thing. The circle, bingo. So we could write it as V squared over R, and then we've got the sum of the forces equals mv squared over r. Well, there's only one force here, so for the sum of the forces, we can use something else. Yeah, and just You totally could. For the Yeah, I have a long playlist of all of our recordings. So literally just yeah, it's literally on YouTube. Just click on that playlist and just have fun, buddy. That's totally a thing. Wait, let's keep going. Let's keep going. There's one force. What is that force? There we go. So don't say Tx, right? It's going to be T cosine theta. Okay? So if we want to find, there's two different ways to find the tension. We could actually find the tension both ways here. So if you wanted to find the tension in the x direction, you could say that's mv squared over r cosine theta. Okay? Now, if you want the big brain moment, the the super big brain moment is, hey, isn't this tension? Hey, isn't this tension? So those two things are actually equal to each other. Okay? Yes, and all of the above that y'all just said. Yeah, these two things are actually equal to each other. So if we had to, we could actually use the tension and just set both of these equal to each other and say mg over sine theta is equal to mv squared over r cosine theta. And we could do some simplifications. The biggest one that I see right now, yeah, everybody brought mass to the party, so that mass can go away. So we can cancel the mass on the left hand and the right hand side. There's a couple of other things that we can do. Let's see. If we want to solve, let's say that, I don't know, because the radius is pretty easy to find on something going in a circle. The angle might not be as easy, and the velocity is probably a little bit tougher to find as well too. So I'm going to try to solve this for the velocity. Cross multiply exactly is what we should do. I'm going to take that r cosine theta and I'm going to bring it over here. Uh, so that's gr cosine theta over sine theta is equal to v squared. Okay, now there's two more things that we could do, but that's okay. Yeah, we can take the square root. So we can't kill theta because let's not use the word kill. We can't cancel out theta. Yeah, yeah, because cosine and sine aren't the same thing. Those are two different operations, so we can't do that. But we can say that the velocity would be gr cosine theta over sine theta, and we could totally use that. Um, we know g. All we would need here is the radius and the angle, and we're good. Um, there is one more thing which may be useful to you guys for the ACT. So if you remember the cosine of theta over the sine of theta, using some fancy mumbo jumbo that we're not really going to talk about, is equal to the cotangent of theta. So we could actually just change this whole thing and make it gr cotangent theta. You don't have to remember that. There's also one more thing for the ACT. If you have sine theta over cosine theta, that one is equal to the tangent of theta. And that is totally true in either case. Do y'all even know what a cotangent is? Okay. Cotangent is what happens whenever you flip over the tangent. So yeah, so like if you know your SOHCAHTOA, it's not -1. -1 is the inverse. Okay, so SOHCAH, it is not the same difference. It is the reciprocal. There's a difference between inverse and reciprocal. So yeah, you get a very different answer. Tangent is equal to opposite over adjacent. So the cotangent just flips it over. It's adjacent over opposite. Okay, and you can kind of see that as well too. Well, I mean, look at this. Tangent is sine over cosine. So cotangent is just these two things flipped over. Tangent is sine over cosine, so therefore cotangent is cosine over sine. Good luck. I don't know how you like. If you just gave up on those, you would use the Pythagorean theorem for everything, and that would just everybody would laugh at you. Like sine, cosine, and tangent are the engineer way to do things. That's like the shortcut method is using sine, cosine, and tangent. I promise. Otherwise, it's similar triangles all the way down, and that gets maddening real quick. That's like crazy mode. Okay, so that was a little crazy with the. Oh, by the way, this thing. This guy down here. That would be an expression if we needed to find out what the velocity was. Yeah. This thing is called a conical pendulum. Okay. This thing is called a conical pendulum. If it's drooping down, that's a conical pendulum. So you might actually see that happen a couple of times. Next in line, what if your circle is not horizontal? What if your circle is vertical? Okay. Like an airplane or a roller coaster loop-de-loop. Okay. So if there's a track going this way and it goes around and it loops over, goes up to the top and then back down, and then that's it. It's motorized there. Look at these poor innocent people, and they're gonna what? No, oh, they're circular this time. They're circular this time. They're circular this time. They're totally circular this time. This problem says that it's a circle. I don't know what's going on here. All right, so like before we even go in the circle, if yeah, go for it. Before we even go in a circle, if this thing is like just moving, what force? Let's say it's moving at a constant speed. What forces do we have acting on it? We have a normal force, right? So we have normal, and we also have gravity, mg going down. Okay, so like we're going to assume that we have an applied force pushing it forward and that we have an equal frictional force pulling it backwards. Okay, that's fine by me, and that's okay. We're going to assume that through this entire process that the applied force and the frictional force end up canceling each other out. They stay the same. Okay. So, and we're going to be going in a circle. Now, whenever we go in a circle, our line of action, instead of going this way, our line of action is going to like follow the circle all the way around. So what that means is that at any point in the circle itself, your line of action is automatically like curving with that circle. So as you continue to move around, you're actually going to slide your vectors and go across. So if we move to this particular location, like right here, um, the line of action is going to be going down like this, right, straight down. So mg is pointing straight down like this, right? Your applied force is going to have to be going like parallel to the line of action. So we're going to have a force applied and a force of friction. So these two things are sliding. But I can't slide gravity. I can't just take the Earth with me and just go like, "Yeet boy, we're going this way," and tilt it to the side. That's not happening. That's not going to end up happening. Same thing with the normal force. I can't really like. I guess it is kind of going with us though, because if you got this applied force right here, the normal force is always going to be 90 degrees to the surface. So you can kind of see that most of these arrows stay the same and they just kind of rotate with it, except for gravity. Okay, all of these arrows stay the same except for gravity. Okay, this is why you kind of feel weightless at the top. So like if you're ever on a loop-de-loop on a roller coaster and you get to the very, very top, then you kind of feel this like weird sensation of like, oh my gosh, I'm gonna fall kind of thing. Okay, no? What do you feel? Well, I mean, like, I know, but you, okay, like normally people go on roller coaster rides to feel something, right? You're not just like on a roller coaster ride and be like, this is a completely normal experience. This is just like riding in the car at 72 miles per hour. I'm ready to go. I just hear the white noise. No, there's forces going around like all over the place, and everything's moving really fast. When you make it to the very top, then you have this feeling, okay, this weird feeling, this weird sensation that like you're like dropping, okay? Right. I understand that you want to sleep, but at the same time, even on a roller coaster, you gotta feel something. I don't know. I've never seen somebody on a roller coaster just vibing, but I guess it's a thing. If you're at the very, very top, something really interesting happens. No. No. That is not how that works. gravity is going down as always, and normal force is pointing in the same direction. Okay, so you still have your applied force and you still have your frictional force. They're still going at, force of friction going this way and the applied force going this way. But your normal force and your mg force, these two are actually working together with each other. Okay, yeah, because like this actually keeps you in the circle. Okay. Oh, prizes. It's prize week. I think I'm gonna go ahead and stop here because I think we've only got 3 minutes left, so we'll pick this up on Monday.